So then let's maybe get started. So we have 15, I hope, exciting minutes to show you how to scale PyTorch model training with minimal code changes. So here I'm just showing you a baseline. It looks not so pretty. We will get to what that means in a few minutes. But so what I'm showing you here is training a vision transformer from scratch, where I'm using a simple vision transformer. So which type of vision transformer, I would say for the sake of the example, doesn't matter that much. But I have code examples where I can dive more into the details if you're curious. So the main takeaway here, though, is for this particular code example, it took 60 minutes to train it from scratch, and it achieved an accuracy of 62.85%, which is not very impressive. So the goal of this talk is essentially to improve that, both in terms of the accuracy and, of course, in terms of the training time that it takes to train this model. So all the code examples also that I'm showing you are here on GitHub. So of course, I will only briefly talk about the results, but if you want to reuse any of the code or check it out in detail, run it on your own computer, it's all here on GitHub if you want to check that out later. So one of the main points I wanted to make before we dive into some details here is I just showed you some code for training a vision transformer from scratch. And one of the things in 2023 now, or maybe even 2022, is the theme that training from scratch doesn't really make that much sense anymore. In terms of usually vision transformers use a lot of data, and they are usually generally useful if we pre-train them. For many applications, it doesn't make sense to really train them from scratch. So what makes more sense is to fine-tune them. So you download a vision transformer that is already pre-trained on a large data set, and then you fine-tune them. It's similar to what we do also with large language models, but of course this is a vision conference, so I'm using a vision transformer here. And when I do that, I use the same vision transformer. Now it's pre-trained on ImageNet. Now I do the training here, and you can see it reaches 95% accuracy, and I only need 3 epochs. So before I needed here 10 epochs, and it didn't really improve that much more after 10 epochs if you would train it longer. And it takes, of course, more time, so we can get the same, way better performance in a third of the time here. So that is already one improvement. Now, the rest of this talk is essentially how we can make this faster. So I'm using a very simple vision transformer here for the sake of the example, so you can run it, let's say, also relatively quickly on your own computer. But of course, the same concept applies to larger vision transformers as well. I just picked a simpler example, so it can run on any computer. But of course, this translates to larger problems as well. So here's the same thing, just showing you what I just compared, let's say, in a more pretty format. So on the left-hand side, we see basically that the fine-tuning is better than the training from scratch in terms of accuracy. And it cuts down the time, the training time, by a lot. So here, the larger is better, and here, the smaller is better. So now the question is essentially, how can we accelerate that even further without, let's say, having to put too much effort into changing our code here? So one of the libraries that I use a lot is Fabric, which is essentially like a fast, easy, and convenient way to scale PyTorch code by making only a few changes in the code, like 3-4 lines of code without, let's say, much effort. It takes like 3 minutes or so. And it's essentially bringing more advanced functionality to PyTorch that is already available in PyTorch, but just complicated to use. So like a person who likes, like me, who likes to get things done, I like to have that very convenient and easy accessible. And I put an asterisk here on Fabric because there is one little catch. And the catch is that it's a free and open source library, so it doesn't cost any money, nothing. It's open source, it's freely available, and it's on top of PyTorch. It's essentially, you can think of it as an API on top of PyTorch. And you can install it or use it from Lightning. You do pip install Lightning, and then you can import Fabric import Lightning Fabric as Fabric, essentially. So I'm showing you now the little code changes you have to make, and then how it improves, let's say, the runtime of our vision transformer here. So here's just a regular PyTorch script, just the abstract version of a PyTorch script, where you have a PyTorch model. It can be any model, for example, our vision transformer. You define your PyTorch dataset, and then it's the typical forward pass in PyTorch. So the details don't really matter here, but this is like what you would usually do when you code something just using pure PyTorch in, let's say, a more abstract way. And then when we use Fabric, so this looks like a lot of information. I will go through it step by step in a few moments. But what you have to do is essentially only changing a few lines of code. So you import Fabric, you add these 2 lines of code, and then you call setup on the model and the data loaders to bring them on the same device. For example, if you train on a GPU, that they are sitting on the same device. And then the only real change you have to make is calling fabric.backward loss instead of loss.backward. And these are the only changes you really have to make if you take an existing PyTorch script and convert it to Fabric here. So, and just to do it a little bit more slowly, like step by step. So the first thing is instantiating Fabric. So we import it, instantiate it. The second step is setting up the model and the optimizer. And the third step is using fabric.backward. And that's really these three things, the only things you have to do. And then you can, I will show you in a few moments, access more advanced functionality. So here's first a baseline. So when I convert my PyTorch script using Fabric, like these little changes, you can see it doesn't really affect the runtime. The runtime is the same. There's maybe a little slight differences just due to random fluctuation. So if you run the code twice, you always get like, I don't know, like a few seconds difference because of the machine. You can maybe run that 100 times on average, then it should be exactly the same. And you can also see accuracy-wise, there's no change. So what I'm trying to show you is that when you use Fabric, there's no, let's say, penalty or no advantage because we are exactly running the same model in the same way, just a little bit of code change here. Now, the cool thing is that we can now access more advanced functionality. So here what I'm doing is mixed precision training. So you can see using mixed precision training, I run the same code 3 times faster while maintaining the same accuracy. And this is on one GPU. Using mixed precision training, I can 3 times increase the speed of my model training. So and how I do that, what I showed you with Fabric, once we have this Fabric script, we only have to add one thing here, precision BF16 mixed. So, and that's it. So it's one little word. It's not even one line of code that we have to change. It's maybe 1/2 or 1/3 of a line of code that we have to change. So it's pretty straightforward. And if you are wondering what BF16 means, that means a brain float 16. So maybe just briefly what that means is usually when we train models on a GPU, we use 32-bit precision. But in recent times, to, let's say, accelerate the training and to cut down the memory required on the GPU, we also tend to nowadays use float 16 precision. So float 16 has a little bit less precision, half the precision as float 32, of course. And essentially, you are more like approximating the loss, but for deep learning models, it's usually sufficient. So you can get good performance with that. And bfloat 16 is a special, let's say, version of float 16, where you get basically less precision after the decimal point, but you can show larger numbers. So in float 16, the largest number I think is 77,000. If you exceed that number, you get an infinity. Or if you exceed minus 77,000, you also get like a NAN or something like that. So with bfloat 16, you can have larger numbers, exactly the same size of the numbers as with float 32. The downside is that you have less precision after the decimal point. But for most deep learning applications, that works just fine. So I showed you, you get the same training accuracy, but it cuts down the time that it takes to train the model. I should say not every GPU supports brain float 16. So I think it's like the A100s, H100s, and so forth. If you have an older GPU, you can just use a float 16. It also most of the time works fine. So personally, it depends really on what type of model I train. If I notice for LLMs, for example, I often need bfloat 16 to have it converge, but often also float 16 works just fine. So mixed precision training, though, is a little bit different from pure precision training. So how it works, how you can maintain the accuracy is the performance of the model is by starting with a 32-bit weights, then you convert it to these float 16 or bfloat 16 weights, compute the gradients in that lower bit precision, and then you convert the gradients to 32 bits, apply the weight updates, and then you go back and forth. And that's why it's called a mixed precision and not 16 precision. But you can, of course, also try 16-bit precision. But this is usually, I would say, something to try first if your GPU memory supports that, because there you can often maintain the same performance of the model as if you would use 32-bit accuracy. So yeah, I just showed you how we can improve the model performance by using mixed precision training. So another trick is using multiple GPUs. Of course, this only works if you have the hardware, if you have multiple GPUs. But so when I was a PhD student back then, for example, I usually trained one model per GPU because it was quite tricky to set up distributed computing in the local machines or cluster. And with Fabric, this is also now easier. I mean, you can do that in pure PyTorch, but it is more work. Actually, on the PyTorch website, they have a YouTube playlist with 10 videos to watch to get started with fully data parallelism, which is great, but it is, let's say, for someone who doesn't have much time to go through all of that and set it up, it's more work. So I wanted to show you how to do that more, let's say, easily with Fabric. And so I wanted to show or explain to you briefly what fully sharded data parallelism is. So there are multiple ways we can do multi-GPU training. So the traditional way is model parallelism, where in model parallelism, we split the model into chunks. We put each chunk on a different GPU. But it's usually a sequential process where you, let's say, put the first 5 layers on one GPU, the second part of the model on the next GPU, and so forth. And it's a sequential process where you have a bottleneck where you have to wait for the first GPU to finish before the second GPU can take the output of the first GPU, and so forth. Another way is data parallelism, where it's a bit different. So instead of chunking the model, you are chunking the mini batches into micro batches. So each GPU gets a copy of the model and then has a subset of the data set and then training it in parallel and then averaging the gradients and combining them. So that is another way of taking advantage of multiple GPUs. There's pipeline parallelism, which is essentially like optimizing the waiting time between model parallelism and data parallelism. There is sequence parallelism, which is a special case for transformers where you chunk the input sequence. And the most, I would say, nowadays, one of the most important aspects I wanted to get at is a tensor parallelism, where oftentimes we work with large models, LLMs or vision transformers that don't fit on a single GPU anymore. So I just mentioned for data parallelism, each GPU gets a copy of the model, but often these models are too large, so you can't give each GPU a copy. So what you're doing in tensor parallelism is you're chunking the large matrix multiplications or the weights and distribute for each layer the weights across GPUs. So how you can think of this is if you are familiar with, I will show you in a moment. So fully sharded data parallelism, to take a step back, is basically using these two techniques. And I will briefly show you how that works and how you can think of tensor parallelism of sharding the weights onto, let's say, different GPUs. So again, with data parallelism, you split the batch into mini batches, and each model so each GPU gets a copy of the model and trains on the subset of the data set, essentially. For tensor parallelism, you are sharding the layers so that each GPU gets, let's say, half of the weights. So if you have 4 GPUs, each GPU would get 1/4 of the weights and so forth. So roughly you can think of it like that. And if you think of how matrix multiplication works, so each matrix multiplication, you can think of it as multiple dot products, and all of them can be computed independently. So here I'm showing you a simple 2x3 matrix times 3x2. And we can actually distribute this computation. So we can have this matrix multiplication times this vector, and then this one here at the bottom. So we can do those independently on 2 different GPUs, and then we can combine the results. So in this way, that's how tensor parallelism works. You are basically breaking up this multiplication into 2 smaller ones and do that on separate GPUs. And that allows you to train very large models that usually won't fit on a single GPU. And this sounds probably a lot of very complicated, a lot of information. And it intuitively sounds like it's something very complicated to do in PyTorch. But with fully sharded data parallelism, for example, we can do that really, again, with one line of code. So if we have our Fabric set up here, the only thing we have to change is, we define how many devices we want. This depends, of course, how many GPUs you have in your machine. But then you can define the number of devices, set, let's say, fully sharded data parallelism, and it will take care of it for you. So it will then train on multiple GPUs. And fully sharded data parallelism is just one example. You can also put in a deep speed stage 2, stage 3, CPU offloading with deep speed. So there are multiple different arguments you can put here to really access more advanced features that would be, let's say, tedious if you have to do them by hand in PyTorch. So if you have this Fabric set up, you can really just, with one line of code here, make this little change. And if I'm training this model now on 4 GPUs, you can see the time goes down to roughly, I think it's 2 minutes. So we started with 20 minutes, 18.7 minutes, something like that. We went down to 6 minutes with mixed precision training. And then if you have multiple GPUs, you can take advantage of them by using, for example, fully sharded data parallelism and cut it down to 2 minutes. So we went basically from 20 to 2 minutes, like a 10 times improvement. And you can see the accuracy of the model is exactly the same. So you're not really sacrificing anything here. You're accelerating things without getting a penalty in terms of how well the model performs. And yeah, with that, it was just a quick 15-minute overview of, let's say, how you can use Fabric to scale your PyTorch training using mixed precision training and multi-GPU training. Of course, there are advanced features. So if you are curious, we have the booth over there if you want to check more. But yeah, also if you want to check out the code examples, they are here on GitHub. If you want to reach out, here's where you can find me. And yeah, I'm not sure if we have time for questions, but this would be it for this short talk. And I appreciate you attending. It was nice talking to everyone here. Basically, we will chat more, I guess, at the booth. Yeah, thanks for coming.